Alright, so what I want to look at right now is sequences and series. I'm going to begin that by looking at our formula sheet and making some other notes that are useful just in terms of being able to use the formula sheet. So, on your formula sheet you'll see some things. Up at the top you see some geometric formulas, which may or may not be useful during your SOL. Then you see the quadratic formula. Quadratic formula most definitely you will need to use. Now you see here I've added as something that I thought would be useful, the factorization of a sum or difference of cubes. This is something, again, that I would stress to you, something worth adding to your formula sheet because you know that this will come up for sure. As I move down, I see the statistics formulas. Well, this right here tells me how to find a z-score. And if I were to open up my formula sheet, inside I would find the table of z probabilities. Now, you may have to use that, you might not. But in all likelihood, you will have to know that within 1 standard deviation, within 2 standard deviations, and within 3 standard deviations of the mean for a normal distribution, you will have 68%, 95%, and 99.7% of the data. So I just wrote this down as a guideline. Again, something you can add that you know that you can use. Over here are permutations and combinations formulas. Truthfully, I wouldn't really worry about these. We didn't spend time talking about simplifying these factorials or anything like that. I would just stick to your calculator. Remember, you're going to use the calculator, and under the calculator, this is under math probability. And of course, be careful about entering stuff in correctly because you need to enter in n choose r. And on most of our calculators, that requires us to enter n and then go to math probability and get either NPR or NCR, whichever we need for that particular problem. Down here are the sequences and series formulas. So what we're going to focus on is just the simplest problems, the ones that appear to be on the SOL. I am not going to extend this into the more advanced problems. I'm just going to focus again on what appears to be most important. So we could have all sorts of sequences and series, but what we're focusing on are arithmetic and geometric sequences and series. In an arithmetic sequence, I'm adding or subtracting continually by the same value. In a geometric sequence, I am continually multiplying by something. And I could say multiplying or dividing, but it's actually rather essential that when we think of a geometric sequence, rather than saying, oh, I'm dividing by 2 at each step, we really need to be able to think of that as, oh, I'm multiplying by 1/2. And we'll see that as we go through these next several problems. Now, as you look right here, here's an explanation of what each of these things stands for. A sub n is the value of the nth term. S sub n, the sum of the first n terms. S infinity, the sum of an infinite geometric series. These right here are series formulas, or at least the notation. The actual formulas are down here. R is the common ratio, which is for a geometric sequence, and D is the common difference for a arithmetic sequence. Down here I see the actual formulas that I will use as I work through these things. This is how I find the nth term of an arithmetic sequence, that's for geometric, and my sums, and so on. I'm not going to explain all of these individually right now because we'll see them as we work through the following problems. However, one thing that we do need to note while we are here, couple things actually. This first row, a sub n equals a1 plus n minus 1d, and a sub 1 equals a1 times r to the n minus 1. Those are what we call our explicit formulas. If I knew either the first term and common difference, if it were an arithmetic sequence, or the first term and common ratio for a geometric sequence, these formulas would allow me to find any particular term. I could find the 115th term if that's what I was asked. Now below this, I see two different formulas, for arithmetic and geometric sequences. A sub n is equal to a sub n minus 1 plus d, and for geometric I see a sub n is equal to a sub n minus 1 times r. But let's recall that these are recursive formulas. It's telling me I take the previous term. That's what each of these represent. Whatever a sub n is, a sub n minus 1 is what comes before. So this tells me to take the previous term and add the difference, or take the previous term and multiply by the ratio. Now in this video I'm not really going to focus on recursion because I don't know to what end, if any, it appears on the SOL. No questions have been released regarding it. It could show up, it might not. I don't know. Below this, I see sum formulas. Now, for the geometric sequences and series, there are two distinct sum formulas. This is the sum of a finite geometric series, and this is the sum of an infinite geometric series. You notice here r cannot be 1, because then I would have division by 0. And for an infinite geometric series, absolute r has to be less than 1. This is what we talked about with convergence versus divergence. If absolute r were not less than 1, then what I would have is a divergent geometric series, meaning as I added infinitely more terms, the sum would not converge to a particular value. It would instead grow in its magnitude. For the arithmetic series, I see two formulas that are really equivalent. They work slightly differently, but again, they find exactly the same thing. S sub n is n over 2 times a1 plus an, and S sub n is n over 2 times 2a1 plus n minus 1 times d. These can both be useful. This is useful if I know both the first and the last term of whatever I'm adding. This is more useful if I don't know that last term. Okay? So, we're going to use these formulas as we work through these next several problems. All right? I'm going to go ahead and flip to these problems which I've printed out. So again, pause to copy these down, rewind as necessary. I want the 60th term of this sequence. Well, when you're looking at sequence and series, what you really have to look at is what pattern is going on. What am I doing from term to term? And how we figure that out is typically looking at two things. Am I consistently adding or subtracting something? Or failing that, am I multiplying by something at each step? Well, here, if I look at 59, 53, 47, 41, I can see very easily that what's happening is 6 is being subtracted between each of these numbers. And if I consistently subtract or add the same value, that makes this an arithmetic sequence with a common difference of negative 6. Again, pay attention to your signs. If you didn't make this a negative 6, it would invariably mess up your answer. All right. Now, again, if you refer back to your formula sheet, which I just have right here at my side, you'll see that this is the rule for the nth term of an arithmetic sequence. Essentially, we need to find that in order to answer our question. Okay? So this is the nth term of a sequence, of an arithmetic sequence. Well, the first term I can see is 59. We've determined that the common difference is negative 6. Okay. All right. If I specifically ask you to find the rule for this sequence, here's where we would talk about distributing and simplifying this. If I'm just asking you for the 60th term, that's really an unnecessary step. I can just go right off of this if I want to find the 60th term. If I want to find the 60th term, I can talk about a sub 60. So I can write that as 59 plus n minus 1. Well, if I'm talking about a sub 60, that means n is 60. And then I actually need to go ahead and start simplifying this expression. So this is 59 plus 59 times negative 6. Okay, well, 59 times negative 6 is negative 354. That is 59 times negative 6. All right, and if I subtract these, what I will get is negative 295. So the 60th term of this sequence is negative 295. And I can thusly stop. I found the 60th term, and I can move on to the next problem. Here, I'm asked for the 9th term of this sequence. Well, here, I want to look at what's going on. Now, I would first probably check and see, well, am I consistently adding or subtracting something? Well, if I were consistently adding or subtracting something, it would be very difficult to go from some number of ninths to some number of thirds to an integer to a different integer. So that is probably not the case here. So instead, what's probably going on is I'm multiplying by something. So what I need to look at is what's the ratio of these terms. Now to find a ratio, I can take any term and divide by what came before it. For example, A2 divided by A1 is the ratio for any geometric sequence. So here, that would mean I would take negative 5/3 and divide that by negative 5/9. Okay? Now, you can, of course, plug that into a calculator. If you use enough parentheses, it'll work. I'll show you how to do that mathematically right here. Dividing by a fraction means, of course, I'm multiplying by its reciprocal. And I can see that what's going on here is my ratio is, in fact, 3. So this is a geometric sequence with a ratio of 3. And again, I could have found that I didn't just have to use A2 and A1. I could have just as easily used A3 and A2, or most obviously, negative 15 divided by negative 5 would have also given me 3. But now that I know my ratio, again, I'm going to write the rule for this sequence so that I can find the 9th term. Referring back to my formula sheet, the nth term of a geometric sequence is a sub n is a1 times r to the n minus 1. Well, my first term is negative 5/9. And my ratio is positive 3. And this will be raised to the n minus 1. So when I want the 9th term, I'm going to substitute. Three to the 9 minus 1. Well, 3 to the 9 minus 1 is 3 to the 8th. 3 to the 8th, I'll double check that real quick with my calculator, is what? 3 to the 8th is 6,561. All right, so what I'm looking at right here is negative 5/9 times 6,561. Now, of course, if you're trying to do the math by hand, it makes more sense to, instead of actually figuring out what 3 to the 8th is, to simplify it with that 9 first. But we'll just forget that. We'll just do it the most accurate way we know how, using the calculator to avoid any mistakes. So if I take negative 5/9 and multiply that by 6,561, really I could have just multiplied in 3/8 right on the calculator. Not 3/8, 3 to the 8th, excuse me. And there's a syntax error. Oh, so good lesson right here. What was my error? See how long this is? That's a subtraction, not a negative. So what I'm going to do is pull up that entry and just fix that one thing. I'm going to hit second enter, pull up what I just did, and change that to a negative. And then my calculator is happy. The 9th term is negative 3,645. Okay. So again, what you had to do here was first determine that this is indeed geometric with a ratio of 3. Once I knew that, I used the rule that was given to me that the nth term of a geometric sequence is the first term times r to the n minus 1. I substituted in my values. Negative 5/9 is the first term. The ratio is 3 to the n minus 1. And then when I substituted in, 9 minus 1 is 8, and I have negative 5/9 times 3 to the 8th. Negative 5/9 times 3 to the 8th is negative 3,645. All right, what about after that? Here I'm asked for the 46th term of an arithmetic sequence with a first term 5 and a common difference 7. Well, you're told that it's arithmetic. You're told the first term is 5. You're told the common difference is 7. All of that is extremely relevant information. What's more, I'm told, most importantly perhaps, that I want the 46th term. So, again, for an arithmetic sequence, I know that the rule is I take the first term plus n minus 1 times the difference. Okay? So, I'll write the general rule before I substitute in n. The first term is 5. The common difference is 7, meaning positive 7. If I want the 46th term, that means n is 46. So this gives me 5 plus 45 times 7. Now 45 times 7 is 315. So 5 plus 315, the 46th term of this sequence is 320. And thus I have the 46th term. Ultimately, once you understand how to use these rules and you understand that that's basically what you're going to be doing for any of these, there's not a whole lot going on with most of these problems. Now let's go ahead and move on. I'm going to change this up a little bit now. This next question asks, what is the sum of the first 26 terms of this sequence? Now, this is not ultimately that challenging, but the phrasing of it is really testing, do you understand? It says sequence, but it also says sum. What we need to understand is that whenever I say the sum of a sequence, what I'm referring to is a series. So the question is, what's going on with these numbers here? What's going on? Is it arithmetic? Is it geometric? How do I move from 1/3 to 5/3 to 3 to 13/3, etc.? Well, from 1/3 to 5/3, I can figure out that I'm adding 4/3. And I can see the same thing here from 13/3 to 17/3. That's also plus 4/3. But in the middle here, I see 3, and I'm a little bit less sure. Well, let's remember, 3 itself is how many thirds? 3, if I multiply by 3 over 3, is actually 9/3. Now, this makes sense. If I go from 1/3 to 5/3 to 9/3 to 13/3 to 17/3 to 21/3, then I'm consistently adding 4/3. And I don't need to write that anymore. This is clearly arithmetic with a common difference of 4/3. All right. So it asks me to find the sum of the first 26 terms. Now, if I go to my formula sheet, I see two rules. The first one is this. The sum of the first n terms of an arithmetic sequence is n over 2 times a1 plus an. The second form I see is this, n over 2 times 2a1 plus n minus 1 d. Now, I made reference to this earlier. This one right here would be very easily used if I knew what an was. But I don't know what the 26th term is. Could I find it? Of course. I could write a rule, figure out what the 26th term is, and use this. And that would be all well and good. But this second formula here will actually be much more advantageous. I know what the first term is, I've determined the difference, and we were told specifically the first 26 terms. So that means 26 will be my n. So I'm going to use this second formula. S26 will equal 26 over 2, and they use brackets here. It really doesn't matter. It's just to differentiate from the parentheses that are right there. The first term is 1/3, and I'm multiplying 26 minus 1 times a difference of 4/3. Make that a bracket to balance out with what I already had. All right, now I need to simplify this. 26 over 2, I can do that easily. That's 13. 2 times 1/3 is 2/3. This right here, 26 minus 1, I know is 25. So if I do 25 times 4/3, I know I multiply the 25 into the numerator and get 100 thirds. So I'm going to work to the side right now because I've run out of my workspace. But I have 13 times 2/3 plus 100 thirds is 102 thirds. Now 3 goes into 102 exactly 34 times. So this is 13 times 34. 13 times 34, if we go ahead and multiply that, I'll go ahead and use the calculator, we get 442. And thus, we have our answer. This original sequence that was given to us, 1/3, 5/3, 3, 13/3, 17/3, 7, etc. If I took the first 26 terms of this sequence and added them, in other words, if I took a series of these, then what I would get is a sum of 442. And I did this, again, using just the knowledge that this was arithmetic and I was consistently adding 4/3 and formulas that were given to me. I used the second formula because I did not know the 26th term. If I had found it, I could have used this just as easily. Let's move on. Here, I'm asked to evaluate the sum 6 plus 12 plus 24 plus, and then there's an ellipsis, and it says plus 1536. Well, this is again a series. Is it geometric or is it arithmetic? Well, a quick inspection says that from 6 to 12 I multiply by 2. From 12 to 24, again, I multiply by 2. And then at some point I will get 1,536. The question is, when? I know that 6 is my first term. I don't know what term this is. So I have to do a little bit of work here. I know that I'm trying to find a sum. The sum of a geometric series is the first term times 1 minus r to the n over 1 minus r. Now I already know the first term is 6, I know the ratio is 2, but I do need to know what n is. So the question again remains, when does 1,536 come up in this pattern? And for that I need to go back and say, what is the rule for this geometric sequence? So it's a1 times r to the n minus 1. First term is 6, the ratio is 2, I'll just write this with parentheses, to the n minus 1. Now what I know is that at some point 1,536 comes up in this pattern. If I divide both sides by 6, then I can isolate the exponential and I'll be able to solve this. Well, 6 goes into 1,536, let's see here, 256 times. All right. Why is this significant? How can I use this? Well, if I'm trying to solve an exponential equation, the best way to do that is to figure out, is 256 a power of 2? And the answer is yes. Now, if you don't already know what power of 256 is, you can work at it a little bit, and without too much trouble, you can figure out that 256 is in fact 2 to the 8th. So if 2 to the 8th is equal to 2 to the n minus 1, that means that these exponents have to be equal. And in fact, 8 is equal to n minus 1, which means n is 9 when I add 1 to both sides. All right, great. Now I have almost all of the work done, apart from the actual substitution, to figure out this sum. I know now that what I am finding is the sum of the first 9 terms. I will do 6 times 1 minus 2 to the 9th. I'm very careful here to use parentheses. It's more important when your ratio is either a fraction or negative, because the parentheses will significantly influence your answer. Here they end up not doing anything. These ones anyhow. These ones still very important. 2 to the 9th is 512. 1 minus 2 is negative 1. So what I have here is 6 times negative 511 over negative 1. Well, that means if I have a negative over a negative, those two will cancel each other out. And what I would be left with if I multiply 6 by 511 is 3,066. So, if I added up all these terms, if I figured out whatever was missing in there, 24 followed by 48, followed by 96, followed by 192, and so on, the sum of all those would be 3,066. Again, all referring back to using formulas that you know are given to you and are not ultimately that complicated, to be perfectly frank. All right, let's look at the last big thing. Again, these are important. I'm not going to spend time on recursion. I'm not going to spend time on sigma. What I need to spend time on, though, is infinite series. Infinite geometric series. So what I see right here is an infinite geometric series. It tells you it's infinite. If it's going to add, if I'm actually asking you to find the sum, it needs to be geometric. But this is. Now, what the ratio is may not be immediately obvious. So I can find the ratio by taking any term and dividing by what came before it. For example, negative 140 over 350 I know those both have a factor of 10, and 14 over 35, those are both divisible by 7, so this is a ratio of negative 2/5. And you can check, confirm with the calculator that 56 over negative 140 is also negative 2/5. 56 divided by negative 140, and that, of course, if you don't recognize it, is negative 2/5. And you can keep going thusly. So the ratio is negative 2/5. All right? Well, what's the formula for an infinite geometric series? Its sum is equal to simply the first term over 1 minus the ratio. Well, the first term is 350. My ratio is negative 2/5. So since that's negative, I need to use these parentheses. I need to say, oh, this really means 1 plus 2/5. Now 1 plus 2/5, since 1 is 5/5, is actually equal to 7/5. So I have 350 divided by 7/5. And as we know, if I divide by a fraction, that means I'm actually multiplying by its reciprocal. So what I have here is 350 times 5 over 7. All right? Now again, you can do this with a calculator however you're comfortable. If you had wanted to, you could have just taken this right here in parentheses and plugged that into your calculator. Right here, what I know I can do, if I'm thinking of this, doing this by hand, 7 goes into 350 50 times. So this is 50 times 5. 50 times 5 is simply 250. And thus I have the sum. Now again, if I had used the calculator, I would have seen the same thing. 350 divided by, and then in parentheses, I divide by 7/5. And there's 250. But again, when I set this up, it's extremely important to pay attention to various things. How you find the ratio is extremely important. Using the correct sign for the ratio is extremely important. If I had not written negative 2/5, if instead I'd written positive 2/5, my answer would have been completely inaccurate. Let's take a look at one more infinite geometric series right down here. 20 plus 5 plus 5/4 plus 5/16 plus ad infinitum. So again, I want to figure out the ratio. Well, 5 and 20 are my first, 20 and 5 rather, are my first two terms. If I take their ratio, 5 divided by what came before, then my ratio is 1/4. And that makes sense, because if I multiply 5 by 1/4, I get 5/4. If I multiply 5/4 by 1/4, I get 5/16. The next term would be 5/64, and so on. So again, my infinite sum is the first term over 1 minus r. So then, my first term is 20. My ratio is 1/4. 1 minus 1/4, well, 1 is 4/4. If I subtract 1/4, then I get 3/4. As we discussed, if I'm dividing by a fraction, that means I'm actually multiplying by its reciprocal. And I get 20 times 4/3. Well, 20 times 4/3, I know I multiply this into the numerator and get simply 80/3. And it's done. There's nothing more complicated than that. Again, is it possible that you could get harder questions? Maybe. I don't know what they ask. But it's all about reasoning. Mathematics is all about reasoning. And if you understand how these basic formulas work and how to discern if a particular sequence or series is arithmetic or geometric, you have all the tools you need to be successful at this. Again, I hope this has been helpful.